Hiya, I'm Mrs. McTaggart. In this video, we're going to focus on further differentiation. So that involves the chain rule and differentiating all your trig expressions like sine x and cos x. In a separate video, I'll focus on the further integration stuff. So let's have a look. So before I continue, one thing it's worth knowing is I just want to prove to you why you get what you do when you differentiate sine and cos. And the way I'm going to do it is we're going to do it based on the way we teach you how to do the graphs of derivatives. We can do the exact same with sine and cosine. So remember, when you're doing graphs of derivatives, you start with the graph you've got, and wherever you've got a turning point, you trace that right down for a root. So I'm going to trace down this root here at 90, and I'm going to trace down this turning point to be a root at 270. And then anything up to the 90 on your original graph is increasing, so we draw that above. Anything between 90 and 270 was decreasing, so we draw that below. And anything after 270 was increasing, so we draw that above. Now, it's not the best diagram, but what kind of shape is that? It's your hammock shape, isn't it? It's your cosy corner, so that becomes cos x. So the differentiated graph, y dashed, is cos x. All right, let's do the same with the cos one. So again, we've got a turning point here at 0, so that becomes a root at 0. You've got a turning point at 180, which becomes a root at 180. And then you've got a turning point at 360, which becomes a root at 360. Now, anything from 0 to 180, our graph was decreasing, so that bit gets drawn below. And anything after 180, our graph was increasing, so that gets drawn above. And you'll notice that that's an upside down sine graph, which is written as negative sine x. Okay, and I could do the same for differentiating minus sine and minus cos to show you what they come back to, but I don't think I need to. It's sometimes nice to see why this is why it is. Now, I know on your formula sheet it tells you what you get when you differentiate sine and cos, so that's great to look back if you can't remember. But I don't think you need to remember if you can remember this really simple diagram I've got here. So a good friend of mine saw this one year when he was marking higher, and we all thought it was brilliant, and I always teach it now from there on. And I don't think everybody is aware of this. And it's really simple to draw out because you can abbreviate this to SC minus S minus C for quick. And you'll see me doing that when we come to do some questions. Now, we're going to use a wee bit of alliteration here. So there's a good English term. When you're differentiating, you work your way down this list. So D for differentiate, D for down. When you're integrating, you increase. So there's your double I there. So we increase. So for example, differentiating, sine goes to cos, cos goes to sine, sine goes to cos, and then minus sine goes all the way back to the top and becomes sine. When we are integrating, we do it the other way. So integrating, we work our way up. So integrating, minus cos goes to minus sine goes to positive cos, cos goes to sine, and then you've got nowhere to go. Sine comes all the way back to the bottom and goes to cos. So I think this really, really helps, especially when there's the negative ones there as well. And it takes 2 seconds to copy down. So we're going to try some. We're going to differentiate the following. So the first one I want to do is we're going to differentiate 4 sine x. So I'm just going to write out my little thing down here. So sine cos minus sine minus cos. And I think that's really easy to remember because it's just alternating words each time. And we are differentiating, so we are always working our way down the list. Right, so sine, if you look at the list, sine goes to cos. So this just becomes 4 cos x. Now I should have put in the notation, if we're differentiating, that becomes f dashed x in there. So 4 sine goes to 4 cos. There's no numbers in front of the x. That's when you've got to start doing something a wee bit different. So that one's nice and straightforward. Similarly, even though we've got 2 of them in this equation, it's just the exact same. So y differentiated becomes dy by dx. So sine, we've just done, sine goes to cos. So 2 sine becomes 2 cos x. Now this is take away 3 cos x, but what I'm going to do is I'm going to treat that as just negative cos. And then if I'm differentiating, negative cos comes all the way back to the top and becomes positive sine. So that becomes positive 3 sine x. So I don't need to worry about any double negative there. I just took the negative with it, used my little handy table, and we got to there. And that's those two done. Nice and straightforward. Then we've got another style of question. It still involves differentiating, but it's going back to really previous differentiating knowledge. It asks for the equation of a tangent. So anytime you're asked for equation of the tangent or rate of change, remember that just means differentiate. And an equation of a tangent is a straight line. And for a straight line, you need three things. You need a gradient, you need a coordinate or a point, and then you need your equation. And this is just the wee kind of way I always do it, just to remind us of the things we have to do. So step one is get your gradient. A gradient is just dy by dx. So if we differentiate cos, let me see, sine cos minus sine minus cos. Cos differentiated goes to minus sine. So that gives me minus 5 sine x. Now my gradient when x is pi over 2 just means I'm subbing in pi over 2. Now pi over 2 is just 90, so I'm going to just change that to 90. Now from your sine graph, if I quickly draw a wee sketch of it down here, this is your 90 here, and your sine graph is at 1. So we've got minus 5 times 1, which is minus 5. So I'm going to be using gradient as minus 5. Now my coordinate, I already know the x coordinate is pi over 2. So to get the y coordinate, I plug this back into the original. So I'm doing 5 cos of pi over 2, so 5 cos 90. Now cos of 90 is actually your root there. So cos of 90 is 0, so that's just 0. So our coordinate is 0. So what I'm going to do now is I'm going to use these two things. I'm going to use this coordinate and I'm going to use this gradient and I'm going to put them into the equation of a line. So the equation of a line is y minus b. So in this case it'll be y minus 0 is my gradient, bracket x minus pi over 2. And then just multiply that out. I've got negative 5x plus 5 pi over 2. So there is my equation. Okay. Okay, so then you come to this thing called the chain rule. And the chain rule has this really complicated looking wee formula to help you remember it. But when I did higher at school, we learned everything by kind of mantras. And when I teach differentiating, I show you the wee formula of what to do, but then I just keep this wee chant going. And every time I do a question, I'll say times by the power, lower the power. And then the chain rule is just adding on this extra wee bit to it. So we still times by the power, we still lower the power, but now we times by the differentiated bracket. And I'm just going to explain what that is in terms of this notation here. So if you started with a bracket to the power n, step 1 is you times by the power. So there's that bit done. The n at the front is you timesing by the power. Here is the power lowered, and here is the bit where you multiply by the differentiated bracket. Because when you differentiate ax, you get just the a term. Okay, so let's see some of this in action, and you'll see me keep repeating this wee man. So first one, we are going to do f dashed x times by the power becomes 5. You just rewrite your bracket again. So we've times by the power, then we lower the power, and then we multiply by what you get when you differentiate 3x. So 3x differentiated is just 3. You then can tidy this bit up. 5 times 3 is 15. So you have 15 bracket 3x plus 8 all to the power 4. And that's that one done. On the second one, there's a wee bit of prep work involved. I'm going to bring that bracket up to the top. And that's going to become 4x minus 7. And remember, anything with a square root is a power a half. So that's what we're differentiating. So f dashed x equals, so we're going to times by the power, which is a half. We're going to write our bracket. We're going to lower that power to minus 1/2. And then when you differentiate 4x, you get 4. So we times by 4, which is a differentiated bracket. Now the half times the 4 you can do, and that becomes 2. So that gives you 2 times your bracket when it's tidied up. And although the question didn't mention it, but it's always good to have it to rewrite with positive indices. So that would be 2 all over 4x minus 7. And you can either write that as a power of half, or you can put a square root over it all. Your choice, okay? I'm going to leave it as the square root. So here's just a couple more slightly different. So there's a wee bit more of the differentiation involved in these ones. That's why they're a bit trickier. So step 1, times by the power becomes 4. I should be writing f dash x here. That's bad notation. So you've got 4 times your bracket. Lower the power, which becomes 3. And then when you differentiate the bracket, 3x squared becomes, remember, times by the power, lower the power, becomes 6x. Okay? And then we just tidy that up. So 4 times 6 is 24. So you've got 24x bracket 3x squared minus 4, all cubed. And that is that one differentiated. On this one, you've got a wee bit of prep work again. So we're going to write this as x squared plus 6x to the power 1/2. So f dashed x will be times by the power. In fact, I think I'm going to need a wee bit more room for this one. So f dashed x will become times by the power. Write my bracket out. Lower the power, so that goes to minus 1/2. And then when I times by the differentiated bracket, there's going to be more than one term. X squared becomes 2x. 6x becomes 6. So there's a plus 6. Now, normally we tidy up the first thing times the end thing. That second bracket here, everything in there can be multiplied nicely by that half. So I'm going to do that. I'm just going to half those numbers. So this gives me my bracket to the power negative 1/2 times x plus 3. So all I've done is multiplied that bracket through by the half. And then one last little thing to do is I don't like having this bracket with negative powers on the top. So I'm going to put the x plus 3 on the top, and I'm going to take the other bit to the bottom. And power negative 1/2 becomes 1/2. So you can either write this as all to the power 1/2, or you can put the square root over it. I'm just into the habit of always putting the square root, because what if you then had to substitute in here? It's nicer to have it in root form. So that one was a wee bit trickier, a bit more to it. So that was a chain rule for brackets and things. Now we need to look at the chain rule for trig expressions. And it can be used in trig expressions also, just slightly different. We still differentiate the trig part, so that's changing the sine to the cos. But then we have to multiply by the differentiated x term. So see that bit we added in about times by the differentiated bracket? The differentiated bracket this time is you'll have things like sine 3x. So you'd have to think of that as having a wee bracket around it. This is the bit you differentiate and times by. So we would change sine to cos, and then we would differentiate that and get 3 and times by 3. Similarly, this wee bit here is important. If you have any cos with a power, remember that means you've actually got cos x to the power 4. It's not the x that's got the power 4. Common mistakes are to think that that is the same as that, but it's not. That looks like the power 4 is just with the x. The power 4 goes with the cos. That stands for cos times cos times cos times cos. And to be able to apply the chain rule, you have to write it like that. So let's look at some examples. So for each of these, we're going to differentiate them. So to do this, I'm going to just write my wee thing down the corner again. So sine, cos, minus cos. So cos goes to minus sine. So first step is to change that to minus sine 3x. And then when you differentiate 3x, you get 3. So you times that by 3. And that gives you, and you tidy it up, is negative 3 sine 3x. And I should be writing dy by dx. That's as bad of me. Right, the next one, dy by dx equals. Now differentiating sine, using them arrows, sine goes to cos. So this becomes 3 cos 5x. I'm not changing it at all. Not changing the 3 or the 5 anyway. I'm just changing the word. So 3 cos 5x. When you differentiate 5x, you get 5. So you times by 5. And then you tidy that up, and that gives you 15 cos 5x. So when I'm tidying up, I'm really timesing the first thing by the last thing. Now here's a sine with a power. So I'm going to instantly rewrite that as sine x cubed. So f dashed x would be, so it's one with a bracket now. So we times by the power, leave your bracket as is, lower the power. And then we times by the differentiated bracket. When you differentiate, sine goes to cos. So we times by cos x. And then there's different ways of writing this. I would just write it in the order it is, but I'd put the squared back with the sine instead of at the outside, and then cos x. And that's that one done. Okay, and similarly with this other one, we're going to do the same again. I'm just going to rub this out and make a wee bit of room for myself. So I've got sine, cos, minus sine, minus cos. So there's my wee thing to help me. Right, so f dashed x in this case will be times by the power, leave your bracket alone, lower the power. So when you lower the power from being squared, it just becomes a power 1, and I'm just going to write that in for the sake of it just now. And then we times by the differentiated bracket. You can see I'm running out of space here a wee bit. When you differentiate this bracket, there's two things to be wary of. X differentiates to 1. Minus cos goes all the way back to positive sine. So that gives you plus sine 3x. And then you have to differentiate that 3x, so you times it by 3. So if I write this a wee bit nicer, I have got 2 bracket x minus cos 3x. And then my second bracket is 1 plus 3 sine 3x. And I was struggling to fit that one in there. Sorry about that. So it's 1 plus 3 sine 3x. These are getting tricky, aren't they? Okay, so at the end, what I like to do is a couple of past paper questions. So this one here came from 2018. So from 2018, this asks for the rate of change. Now, rate of change just means you want to differentiate and sub in x is 5 pi over 3. So let's have a wee look. So f dashed x, oh wait a minute, I'm going to rewrite this first as 4 sine x cubed. So sine cos minus cos. Right, so differentiate that. So times by the power. So we're timesing the 4 by 3, which is 12. We are going to lower the power to 2. And when you differentiate sine x, you get cos x. So we're going to times that by cos x. Then I'm going to sub in 5 pi over 6. Now 5 pi over 6 is just 5 times 30, which is 150. And I'm going to write in 150 instead. So I've got 12 times sine 150 squared times cos 150. Right, 150. Let's draw our old sine tan cos table. 150 falls here. So we use this angle in here, bringing it to the horizontal, which is 30. Now sine is positive in there, so that's just the same as sine 30. So sine 150 is the same as sine 30. Cos 150, however, cos is negative in that box, so that is the same as negative cos 30. Now let's test your exact values. Sine 30 is a half, so you've got 12 times a half squared times cos of 30 is root 3 over 2, so we've got negative root 3 over 2. So we have 12 times a half is a quarter, and then we have negative root 3 over 2. So from here I'm just going to multiply all the top numbers. 12 times 1 times root 3 is just 12 root 3, but there's a negative there. So negative 12 root 3. And on the bottom you've got 8. And then obviously I can cancel the 12 and the 4. So that gives me 4 times table is negative 3 root 3 all over 8 for that one. Next I've got one from 2019. So this one needs a wee bit of prep before we can differentiate. So this would be 1 minus 3x to the power minus 5 if you bring that to the top. So divide by dx. Let's do the chain rule. So times by the power gives you minus 5. Lower the power goes to minus 6. And then we times by what you get when you differentiate the bracket. Differentiating this minus 3x gives you minus 3. So tidying up, outside things multiply. Minus 5 times minus 3 gives me 15, bracket 1 minus 3x to negative 6. And I like writing things positively, so I'm going to take that to the bottom. And there is your answer for that one. Okay, I've got one more. This has also got a wee element of integration on it, but I think we'll be okay. So for part A, when you differentiate this, you are going to say, right, dy by dx equals times by your power is 1/2. Leave your bracket alone. Lower your power is minus 1/2. And then when you differentiate that bracket, you get x squared becomes 2x. Now, when I'm all tidy this up, your half times 2 just gives you 1. And then you've got an x there. So we end up with x bracket x squared plus 7 all to the power minus 1/2. And then you know I like to write it positively. So we're going to write that as power of half becomes the square root, x squared plus 7. Now, notice on part B, they ask you to then integrate this fraction. Now, that fraction looks very like the answer I've just got. So this here looks very like this here. But what is the only difference? The difference is this number 4, right? Now, technically, that 4 is just a constant that's being multiplied by. So, remember when you integrate, it goes back to what you had before you differentiated. So this is the same as having a 4 out the front of this and asking you to integrate x over this, because then you could just introduce the 4 at the end again. So basically what I'm saying is when we go to try and integrate for part B, it's going to be what they gave you in part A but with a big 4 in front. So part B, the answer is y equals 4 bracket x squared plus 7 to the power 1/2. Thanks very much for watching. I hope this has helped.